Welcome to This Explainer. Today, we are going to completely bypass the science fiction tropes and dissect the harsh reality and the visionary engineering behind building a self-sustaining city on Mars. We're looking strictly at the hard data, the physics, and the mind-bending logistical realities of what it will actually take to put 1 million humans on the red planet. Let's get right into it.
Okay, so here's our structured blueprint for today. We're going to cover 5 key areas. First, the existential stakes, basically why we're even looking at Mars. Second, the transportation, or how we physically get there. Third, the hostile reality waiting for us. Fourth, the survival blueprint. And finally, the human scale.
Starting right off with Section 1, the existential stakes, why we absolutely must become multi-planetary.
Think about this for a second. Earth has been around for 4.5 billion years. But right now, this is literally the very first time in that massive, unimaginable timeline that the technological window of opportunity is actually open to extend life beyond our home planet. We have the capability right now, but we have absolutely zero guarantee on how long this window will stay open.
And that's exactly the core philosophy driving organizations like SpaceX. Think of becoming a multiplanetary species as a massive backup drive for humanity. Earth is vulnerable, guys. From a massive asteroid impact like the one that wiped out the dinosaurs 66 million years ago, to a global conflict, being confined to just a single planet means we're basically sitting around waiting for an eventual extinction event. Colonizing Mars is quite literally an insurance policy to ensure the light of consciousness isn't just extinguished.
Right. Let's move on to Section 2, the transportation, the economics and mechanics of interplanetary travel. Because having the will to go is one thing. Actually paying for it is a whole different ballgame. We are facing a monumental economic hurdle. Right now, if we used our conventional throwaway rocket technology, sending just a single person to Mars would cost an estimated $10 billion. $10 billion. Obviously, that makes colonization fundamentally impossible. To make a self-sustaining city viable, SpaceX's fully reusable Starship, which is this stainless steel behemoth larger than a 747, has to slash that cost by a factor of 50,000. The target is $200,000 a ticket, basically the price of your median house.
But a cheap ticket really doesn't matter if you can't ever come home, right? And you simply cannot carry enough fuel from Earth for a round trip. So, to get back home, the Starship will rely on something called the Sabatier reaction to literally manufacture its methane fuel right there on the Martian surface. It's established chemistry, and it is exactly why Starship runs on methane instead of traditional rocket fuel. So how does that actually work in practice? By targeting the Arcadia region, which is a flat plain we know has subsurface water ice, the very first uncrewed ships will land and roll out mining robots. They'll extract the water ice, pull carbon dioxide right out of the thin Martian air, and use massive solar arrays alongside modular nuclear kilopower to run that Sabatier reaction. They are basically going to establish a working gas station, filling up the return rockets with liquid methane and oxygen long before humans even arrive. Now, even with all this brilliant engineering, traditional chemical propulsion still takes a grueling 80 to 150 days just to reach Mars. But partnering with NASA to develop nuclear thermal propulsion, specifically NASA's Project Draco, could drastically cut down that transit time. By using a small fission reactor to violently heat and expand liquid hydrogen, it essentially acts as a high-tech, steam-powered spaceship, offering 3 to 5 times greater efficiency than our current chemical rockets. Okay, let's pivot to Section 3, the hostile reality, confronting the brutal environment of the red planet. Let's be real. As a vacation destination, Mars leaves a lot to be desired. This table starkly contrasts Earth's cozy environment with the reality waiting for us, because stepping off that rocket is where the true, deadly trials actually begin. Mars has no magnetic field, meaning you're constantly bombarded by dangerous cosmic radiation. The average temperature is a freezing -60 degrees Celsius. And perhaps the most deadly factor, the atmospheric pressure is less than 1% of Earth's. At that pressure, liquid water just cannot exist. If you stepped outside without a pressurized suit, the water inside your body would instantly turn to gas, and your blood would effectively boil, leading to a complete failure of your circulatory system in under a minute. Now look at this atmospheric breakdown. That tiny wisp of an atmosphere is 95% carbon dioxide. It is incredibly toxic for you to breathe. You lose consciousness in seconds. But, interestingly enough, this high concentration of carbon and oxygen is actually super useful. If compressed and regulated inside greenhouses, it makes for a fantastic environment for growing plants.
And hey, if the air doesn't get you, the dirt might. Colonists are going to have to manage intense electrostatic dust storms that can span the entire planet. But this isn't just regular sand. The dust is loaded with perchlorates. These are highly toxic chemical compounds that ruin sensitive equipment and can cause severe lung diseases in humans. Every single airlock and suit is going to need meticulous, rigorous dust mitigation protocols. Which brings us to Section 4, the survival blueprint, the step-by-step construction of a Martian base. So how do we actually survive and build a self-sustaining city in an environment this lethal? It all starts with autonomous fleets. Long before humans show up, robots will land to establish power grids using solar panels and those 10-kilowatt nuclear kilowatt reactors we discussed. Then, using designs like the ones that won NASA's 3D printed habitat challenge, robots will process Martian basalt rock, mix it with bioplastics, and literally 3D print protective, egg-shaped structures layer by layer. This entire process relies on what's defined here, in situ resource utilization, or ISRU. To truly survive and scale up, we have to completely transition away from relying on impossibly expensive supply drops from Earth. We literally have to learn to live strictly off the alien land. The fuel, the water, the breathable air, the very walls of our houses, it all must be synthesized directly from what Mars naturally provides. So what does everyday life actually look like? You definitely won't be living in glass domes on the surface. The radiation is just too high for that. Everyday life will likely involve living mostly in subterranean bases, using the rock itself to block out the cosmic rays. You'll be eating fresh vegetables grown in hydroponic greenhouses, relying on fish farms and lab-grown cultured meat for your protein, and breathing air produced by highly scaled MOXIE units, which are machines that literally pull oxygen right out of the thin CO2 atmosphere. Let's move to our final section, Section 5, the human scale, the massive logistics of interplanetary migration. Our ultimate goal is migrating 1 million people across the solar system. But first, we have to hit a vital threshold, 5,000. That is the absolute minimum number of people needed to ensure a colony has enough genetic diversity, specialization of labor, and skill redundancy just to survive. If a critical water recycler breaks in a colony of 100 people, it could easily be fatal. But a colony of 5,000, it has the resilience and the deep bench of engineers needed to fix it. But the ultimate goal remains 1 million. Getting 1 million people there is strictly dictated by orbital mechanics. Earth and Mars only align perfectly once every 26 months. Miss a launch window and you're stuck waiting 2 whole years. Reaching that 1 million citizen mark will require fleets of 1,000 starships launching all together every 26 months, undertaking 115-day transits for decades. It is a relentless, methodical marathon of sheer logistics. But the true bottleneck might actually be the human body and mind. The human scale of this endeavor means facing severe physical deconditioning. Even with Mars's partial gravity, colonists could face space anemia and a 1 to 2% bone density loss every single month. Then there's the psychological toll. You're living in a 50 square meter confined space, dealing with up to a 22-minute communication delay with Earth each way, and knowing that real-time help or an emergency evacuation is fundamentally impossible. You are entirely on your own. So, knowing all of this, the bone loss, the toxic dust, the boiling temperatures, and the extreme mind-bending isolation, the final provocative question remains. Would you be willing to buy that one-way ticket? Would you trade Earth's oceans, its forests, and all our comforts for a 50 square meter underground box to become a pioneer, leaving absolutely everything behind to be humanity's ultimate insurance policy? It's probably the most profound choice our species has ever generated. Thank you so much for joining me on this explainer, and keep questioning the universe.